So we've been talking about the dot product. So given two vectors, let's say given vectors v and w in Rn, we have v dot w, which is just if v has some terms v1 through vn, and w is w1 to wn, v1 times w1 plus v2 times w2 and so forth. This is just v1 w1 plus v2 w2 and so forth, vn wn. Okay, so last lecture we're interested in this because this was an example of a bilinear form, right? It's linear in the first argument and it's linear in the second argument, so we call it bilinear. What I want to do today is step back and just remind us of some of the nice properties. One of them is bilinear that the dot product has, right? So what can we say about the dot product? Well, the first thing is that it's commutative. It commutes. V dot w is w dot v. Yeah? This is for any v and w in whatever your vector space r to the n, let's say. They commute. Also, it's linear. Well, we know it's linear in both the first and the second, but all I need to say is it's linear in one of the terms. So let me say it's linear like in the second argument. That is v dot with some scalar copy of x plus y is, you can pull out that scalar c of v dot x plus v dot y. All I need to say is it's linear in the second argument. And then I get for free it's bilinear. Why? Because it commutes. So if you want to show it's linear in the first argument, you would just use the commutative property, then use that it's linear in the second, and then bring it back, right? So these two together actually give you that it's bilinear. I mean, I could just say it's bilinear, but I'm trying to make the point that we can be a little bit more conservative when we say, and this falls out. So if that's not clear, let me just make this explicit. If I want to do, cx plus y dot w, the way we do that is first we use the commutative property to say that's w dot cx plus y, and then we use this linear in the second term, so that's c times w dot x plus w dot y. And then we use the commutative property again, right? So this is c x dot w. So w dot x is the same thing as x dot w because it commutes. And w dot y is the same thing as y dot w. So that's how those two properties work together to give you that's also linear in the first argument. Okay, nice. So whenever you have something that's linear in one argument and that's commutative, you actually have it's bilinear. And maybe the last thing I'll say about the dot product, which you use quite a bit in Introduction to Linear Algebra, is that it's positive definite. So we call it positive definite means if you take some vector v and you dot it with itself, this is always going to be a non-negative value. Like just think what this guy is. This is just the first value of v. So v is v1 through vn. That's just v1 times v1, so v1 squared up through vn squared, right? So it's like, yep, that's always non-negative. In fact, something a little bit stronger is true. It's always non-negative and it's equal to 0 only when, if and only if what? Yeah, it's like the only time for a sum of squares to equal 0 is if each value is itself 0, right? Which means v itself must be 0, if and only if v is 0. So this is what I mean by positive definite. It's always positive except for the case where you have the 0 vector, then it comes out to be 0. Okay, this term is used lots of times. You can talk about positive definite matrices, you can talk about all kinds of things being positive definite. But in general, in particular, the dot product is positive definite. So it's like, why is this nice? Well, this kind of then leads into, so it's these properties of the dot product that tell you the dot product's a really useful thing, right? So in your first course in linear algebra, and I suppose also like in multivariable calculus, you like become convinced that like the dot product's really nice. So like what kinds of things does the dot product tell you? Okay, great, orthogonality. So let's get there in a second. In order to have a notion of orthogonality, we're first going to introduce the notion of a length or a magnitude, right? And so one thing you first learn is like the magnitude of a vector can be defined in terms of its dot product. If the magnitude is just v1 squared through vn squared square rooted, we can define this as just the square root of v dot itself, right? So it's like you can use the dot product to figure out what is the length or magnitude of a vector. And then you have this really beautiful result where you're like, if you have two vectors in Rn, v and w, not only can we use the dot product to determine the magnitude of both v and w, we can also use the dot product to figure out the angle between them. So do you remember what this relation was? This is in Rn, right? This is just recalling from your first course in linear algebra, or maybe some multivariable calculus that shows up. What's the relationship between v, w, and this angle in terms of the dot product? V dot w is, you'll have the magnitude of v, you'll have the magnitude of w, and you'll have cosine theta. Cosine theta. Which in particular tells you that if v and w are orthogonal, if your v and w are orthogonal, that is like perpendicular to each other, right? Then what is cosine of theta going to be? Well, cosine of pi over 2 or 90 degrees is 0. So when you have orthogonal vectors, your dot product gives you 0. And I suppose it goes the other way too. Well, you could have v or w be the 0 vector, and then I suppose you could define the 0 vector to be orthogonal to anything. But so what this is saying is the dot product is a way of detecting if something is orthogonal. Or just the trivial 0 vector, right? Okay. So it's really useful in Rn. So what we want to do is we want to ask, can we take this idea of dot product and generalize it to arbitrary vector spaces? And one way we've already started doing this a little bit is it's like, well, you know, like what if my vector space is like some space of polynomials? What if I have like, I don't know, like vectors inside of P3? And so, you know, what is two vectors in P3? Well, maybe like x cubed minus 1 and something like x squared plus 2x plus 1. So those are both vectors in P3. And it's like, well, what does it mean to dot to you know, polynomials? Like, that's kind of weird. Well, the way we were thinking about it before is we say there's a natural map from P3 to R4, where you just remember the basis of P3 the standard basis is 1x, x squared, x cubed. And so then you can just look at your coefficient vector in terms of the basis b. So this guy, for instance, has a coefficient vector of -1, 0 x's, 0 x squareds, and 1 x cubed. This guy has a coefficient vector of 1, 1, 2 x's, 1 x squared, and no x cubes. And then now you're in R4. And so since we're now in R4, we can dot these together, and you can get, just do the regular dot product in Rn. And it comes out to be -1. So it's like we already have that story. You can take any vectors in a finite dimensional vector space, find the coefficient vectors in terms of some standard basis, whatever your basis is, and then find the dot product. But it's like two reasons why this might be unsatisfactory. Reason one is this is dependent upon your choice of basis. If I picked a different basis, these coefficient vectors would be different, right? And so you might worry, like, maybe it's a little bit less interesting, right? Like, it's not so inherent to your vector space. It's kind of just based on whatever your choice of basis is. You could ask, as you change basis, what properties stay the same, what change? Like, those are questions that are good to ask. But like the second and perhaps even more fundamental problem is this only works if you're in a finite dimensional vector space. What if I'm in some vector space like C, the vector space which is all continuous functions, right? So this is my vector space, which is the space of continuous functions. You can add two continuous functions, get a continuous function. You can scale it by a real number. So let's make these like real values. So this is like over R. Still a continuous function. There's a zero function. Like it has all the properties of a vector space. And what if I have just two vectors, which for us would be just two continuous functions, f and g. Maybe f is something like e to the x. Maybe g is something like cosine of x, whatever. Like, what's going to be our notion here that would be analogous to dot product? Because we can't map this down into some nice Rn, R4, R10, or whatever, because this is infinite dimensional. There's a lot of continuous functions, right? It's really big. So what we want to do is we want to ask ourselves, well, can we come up with something that has these same kinds of properties for, say, continuous functions? So let's try and think. I have two continuous functions. I want a way of combining them that's commutative. I want to do something to f and g that commutes, right? So I shouldn't take like f minus g, that's not commutative. Also, I wanted to spit out a real value, right? Like maybe the first thing I should have said about this is the dot product gives you out a scalar. So I want one way of taking these functions, spits out a scalar. I want it to be commutative. I want it to be linear, Maybe just linear in the second term, but then with commutativity, that'll give me it's bilinear. And it should have this nice property of being positive definite. So it's like, what in the world can you do to functions to do all these things? It's like, well, we could do like some kind of evaluation map, and maybe that would give you the first two, evaluate f and g both at 0, and add those values up or something. That would be commutative. That would be linear. But you wouldn't have this positive definite property. If you evaluate a function at 0, it's not necessarily going to be positive, right? Could have come out to be some negative number. So like, what can you possibly do to functions that will satisfy these properties? Well, do you guys have any guesses? Evaluation map doesn't seem like a good one. We're not going to just evaluate them at some number. That doesn't work. What else could you do to some functions? Continuous functions. Nice functions. Just guess things. Take a derivative. Well, no, because I wanted to come out to be a real valued thing, right? It's like, well, take the derivative, then plug in some value, like plug in x equals 0. Yeah, well, I run into the problem here, where this may not, something dot itself would not be non-negative. So, any other thoughts? Well, let me give you one. What we're going to do is we're going to take the antiderivative from, I need to pick, I need to make some choice, from some A to some B. We could do from 0 to 1. I don't care, whatever values you want. Let's do 0 to 1. 0 to 1, as long as it's continuous there. So if these are functions that are continuous everywhere, it's continuous from 0 to 1. If it's only continuous somewhere else, just pick wherever it's continuous. Pick an interval where it's continuous. Find the antiderivative or the definite integral of f of x times g of x dx. I claim this satisfies all my properties. So let's check really fast. Well, first of all, what kind of thing does this spit out? A real number, yeah? Because it's a definite integral. So we'll end up with some value that's real. So that's nice. How about this one? Is it commutative? Does this commute? Well, obviously, right? This is the same thing as just g of x times f of x and calculate its definite integral from 0 to 1 because continuous functions commute because real numbers commute. So it commutes, that's fine. Is it linear? And it's like, what is f of x times, well, let's try it, some scalar times, well, I guess we could write it as like g of x plus h of x. So here I'm trying to see if it's linear in the second argument. It's like, well, this just comes out to be, the inside is linear, right? Multiplication is linear because this is a real valued function. So it's going to come out to be, since real numbers are, since multiplication is linear, this is just c f of x, g of x, just distribute, plus f of x, h of x. So that's good so far. And then we just use the properties of definite integrals. It's like the definite integral of a sum is just the sum of definite integrals. And when you have a scalar inside, you can pull it out. I think we talked about this before, an example like this, where I've made this same point. So that's good. Linear. Well, it's linear in the second argument, and it's commutative, therefore it's bilinear. Last thing is, let's check if it's positive definite. What would be the integral from 0 to 1 of f of x? Now it's like v dot itself. F of x times f of x. That's f of x squared. Well, f of x squared is a non-negative function, right? You add up its area from 0 to 1. So that will come out to be some non-negative value. And then my question is, when is it 0?
F of x has to be 0.
Why?
Because since it's a positive real value or positive continued real value function, then whenever you take the integral anywhere, if it's non-zero, it'll add some area.
Alex?
Well, the example that came to mind is if we take the continuous function negative x from negative infinity to 0, and then have it be 0 from, so a piecewise function, it'll still be continuous, but have it be negative x from negative infinity to 0. have it be 0 from 0 to 1, and then have it be x minus 1 from 1 to infinity. It's continuous.
Oh, you're saying that it has to be exactly 0 on the interval from 0 to 1, but outside of that interval, it could be, you know, other values. True. So okay. So it has to be exactly 0. This will only come out to be 0 if and only if your f of x is identically 0 on, you know, here it's 0, 1. In general, it's going to be whatever a and b you pick, right? Whatever interval a and b. That's a good point. But the point is here, between 0 and 1, it has to be identically 0, because if you had one point that was not 0, by continuity, close by points would also be non-zero, right? Like I can go down really fast, but like as long as you're, you know, if you've done like any kind of real analysis, or if you know like the epsilon delta definition of continuity, it's like you can't just have one point here and then suddenly jump to 0 everywhere else. That wouldn't be continuous. So for this to be continuous, it must have like a whole little section here. I mean, you can go down really rapidly, but must have a whole little section, and then you're like, well, that has some non-zero area, right? So it has to be identically 0. It has to be identically 0 because it's continuous, at least on that interval. Good. Okay. So if you grant that, I mean, you can just say we're just thinking about these functions restricted to the domain 0, 1, or whatever. If you want to do some other domain, 0 to 10, you can just do that definition instead. Okay, so this works. This works. This gives us the properties we care about. Well, should we try one more? I mean, there's other vector spaces we've seen. What if instead of having your vectors be functions, they could, what other kinds of vectors we've seen? Not like things in Rn, not like just functions, what else? What's another vector space we've talked about? Matrices. So let's say you have two vectors, where your vectors now, I'm going to call them A and B, and let's make them matrices. Let's make them m by n matrices, and for simplicity, we'll just keep them to be real valued. It's like, okay, now what can I do to these matrices? Well, there's a lot I want to do. It should be some operation that commutes. It should be linear. It's bilinear. It should be, you know, positive definite. How are we going to do this? And I wanted to come up with a real number. And how do I take two matrices and end up with a real number? Well, first of all, you have a problem where it's like, these matrices are very different sizes. I mean, well, they're the same size, but it's like, because they're the same size, you can't just do like A times B, because you have like an m by n times an m by n. So already it's like, that's not defined. Like, what could I do so I could multiply them? Yeah, if you transpose one of them, well, now it's an n by m. So at least the multiplication here is defined. But the problem is we now end up with an n by n matrix. I don't want to end up with an m by n matrix. I want to end up with a number, a real number. So what do I need to do to this to make it turn into just a real number? How do you turn a matrix into a number? What's some function on a matrix that spits out a number? Determinant's a great idea, but here's the problem. Is the determinant linear? We talked about this before. No. So linearity is going to fail if you use determinant. So what's another function that eats in some matrix and spits out a square matrix now, eats in a square matrix and spits out a number? Trace. Let's try that. Let's try and define it this way. Okay, well, first let's check, is it commutative? So, you know, it's like, so we have the trace of A transpose B, and over here I have the trace of B transpose A. Are those the same thing? Why and why not? Are they the same? What property makes these the same? Yeah, it's like, well, there's something you do to a matrix that keeps the diagonal the same. Let's take in the transpose. In general, if you have some matrix and you take its transpose, the diagonal stays the same, right? And so the trace of the transpose of a matrix is the same as the trace of just a matrix, which means the trace of A transpose B is the same as the trace of A transpose B transpose. But what is A transpose B transpose? Well, now you have to remind yourself the way you do a transpose of a product of matrices is you do first the transpose of the second, then times the transpose of the first. A transpose is A. Right? So here we're using a couple properties of transpose. The diagonal stays the same, and the transpose of a product is you reverse the order, B transpose times A. Okay. So like, yes, it's commutative. So this is pretty promising. Is it linear? Well, we kind of designed it to be linear. The trace is defined to be linear, and so you can check really fast. What is the trace of A transpose times some scalar copy of, I don't know, the matrix? If I use a big C, you might get confused. Let me just say D plus E. It's like, well, you can distribute this, and you can pull out the scalar. So that's just the trace of your scalar of A transpose D plus A transpose E. And we picked trace because trace is a linear operation. This is just the trace of C A transpose D plus the trace of A transpose E. And then it's like, okay, it's a trace of some scalar times a matrix. If you're scaling a matrix, you're scaling everything on the diagonal by C. So it's the sum of all these things scaled by C. So I can factor out the C, and I get C times the trace of A transpose D plus the trace of A transpose E. Okay, it's linear. Linear in the second argument, but then because of commutativity, it's bilinear. What else do we want to check? Positive definite. Now this one might seem like a little bit more challenging. Like, what is the trace of some A transpose times itself, A? It's like, that might throw you off. But here's a trick to help you see it. Let's just think about what this guy actually is. Like, what is this? Well, let's look at an example. Let's say A is some matrix A11, A12, A21, A22, and B is some matrix B11, B12, B21, B22. Then A transpose times B, taking the trace of that, is taking the trace of this transpose, so A11 down A12, A21, and below it A22. Took the transpose of the first one times the second, B11, B12, B21, B22. And let's think about how this works. Matrix multiplication is going to be row times column. That'll give me the top left value of this matrix. And then I want to know what the bottom right value is, because the trace is adding up the diagonal. So it's this first row times this first column. So the trace is going to begin with the top left element on the diagonal, which is just going to be A11, B11 plus A21, B21 plus, that's the top left element. And now I want to do, to get the bottom right, the bottom times the right. That'll give me my other diagonal value. And notice how that comes out. That's just A12, B12 plus A22, B22. And in general, even if you don't have 2 by 2s, pick whatever size. It's like because you take the transpose of this one, it's like the row of the transpose would have been the column of the original. So it's like you're just going to be doing the first column times the first column, plus the second column times the second column, plus the third column times the third column, and so forth, which is exactly just going to give you the sum of, AI, BI, I should say Aij, Bij. So it's just the corresponding values, where your I is just varying over your rows, and your J is just going over your columns, 1 to M, 1 to N. That is, what is this operation really doing? Well, it's like you're just thinking of this matrix as if it had just been a single vector, A11, A12, A21, A22, and dotting it with this other guy, B11, B12, B21, B22. Right? You can think about this operation as being analogous to a dot product inside of some space. These guys would live inside of R4 and R4. In general, it lives inside of Rmn. Because it's just all the values of your matrix lined up into a vector and then dot the other one. But we've already said the dot product satisfies these properties, so will this, right? It's like what is the trace of some matrix A transpose times itself? Well, that's just going to be A11 squared plus, all the way up until the last entry of A, whatever Amn is squared. And then it's like, clearly that's positive definite. It's greater than or equal to 0, and it's only 0 and all values are 0. Okay, I've probably belabored the point a little bit too much, but here's what I've been wanting to say. We started out with the dot product. We said it has these 3 nice properties. And then we looked at other vector spaces, and we said, well, we can find functions that have the same properties. And so what we do in math, it's like, well, if we really care about the dot product, it has these nice properties. There are other things that have the same nice properties. So let's give some name to all of these things. And so what we're going to call this is we're going to call this the inner product. So I'm going to have to erase this, but we remember what the properties are. And so let's give it a name. So here's my definition. Given some vector space V over a field, and for us the field is going to be either the real numbers or the complex numbers. Given some vector space over that field, in inner product, is a function of the form it's going to take two vectors in V and spit out some scalar in your field. And the way we'll typically denote the inner product will be with these fancy brackets. That is, if you take some vector V and W, the inner product will be denoted with these fancy brackets. So it's some function that takes a vector in V and a vector of V, satisfying I'm going to lie to you, but it's for your own good. It should be commutative. VW equals WV. It should be linear in one of the terms. V, okay, let's do some multiple of x plus y. Should be, pull out that scalar C, V's inner product with x, plus V's inner product with y. And it should have this property of being positive definite. VV, the inner product of V and V, gives you the scalar 0, if and only if your V is identically 0. Granted, we saw, okay, maybe it's like on some domain or whatever, right? Like, okay, we can be careful about what we mean by that, but that's the spirit. And just like before, these two properties together give you that, in fact, it's a bilinear form. Okay, I lied. This is almost true. This would be true if we're working over the reals. And all of our motivating examples were over the reals, so it makes sense why we would land at this definition. But we have to be a little bit careful if we're working over the complex numbers. Because as stated, this will lead us to a contradiction. So let me show you the problem. Then I'm going to slightly amend this definition ever so smallly to account for the fact the ground field might be V. So small problem. If V is some vector field over the complex numbers, then what you could do is you could take the inner product of V with itself. But what I'm actually going to do here, and then for some non-zero V, pick some non-zero V, instead of just doing the inner product of V with itself, I'm going to scalar multiply them both by the imaginary unit, I. Well, if V is non-zero, I times V is still non-zero. So you have something with itself. So from the positive definite, we have that, oh, this shouldn't say 0. This is greater than or equal to 0, right? And only 0 if V is 0. But since we said V is non-zero, this should be positive. But then since it's bilinear, linear in both the second and the first, we can pull the I out twice. So if you pull both those i's out, what do you have in front now? A -1, right? So you get a -1 times V. We said V is non-zero, so the inner product of V with itself is positive, which means negative, the inner product of V with itself, will be negative. Ergo, 0 is less than 0. Like, this is bad, right? Like, not good. So What went wrong? It's like, well, we're working with complex numbers, so there's some funny business there. And you might be like, okay, so something with complex numbers, what properties did we use? We used the commutative property, we used bilinearity. So there seems to be something, well, we used all three properties, really. So we're going to have to append one of these. So like, how should we modify this definition? Well, then we think back. How did you define, if you remember, I think you did this, how did you define the dot product over Cn? Do you remember? If I have two vectors, if I have some vector v, which is some, v1 through vn, and some vector w, which is w1 through wn, how did you define v dot w? The same problem comes up in your first course in linear algebra. And so you actually define this in a funny way. You don't define this. You don't define this to simply be the sum of the values vi. You don't write this. You don't write this as just v1, w1 up through v and wn. And you don't write it like that because you want this to be positive definite. Like what is v dot v? If it was just v1 squared up through, v1 squared up through vn squared, that's not necessarily a positive thing. Like, what if these values are i's? We're just complex numbers now, right? This could give you a negative thing. So how do you make sure that's a positive thing? Right. You instead of multiplying them, you take the complex conjugate of one of them. Now we're going to be super confusing because this bar I mean complex conjugate, this bar I mean vectors, right? But what I'm saying here is instead of you don't define this as like v transpose times v. Instead you do the conjugate transpose times v. This is defined to be v conjugate transpose times w. You take the conjugates of one of them. But now you don't actually have that it's commutative anymore. Because v times w comes out to be something different than w times v. W times v as vectors would be the conjugate of v1 times of w1 times v1 up through conjugate of wn times vn. These are not the same thing. Right, we see these are different. We know how complex multiplication works. A plus bi times c plus di. If you take the conjugate of the first one, you have a minus bi times c plus di. If you take the conjugate of the second one, the minus would be there. Right? It's different. So it's like, what's the relationship between these? Well, this guy down here is the complex conjugate of the guy above him. So v dot w is the complex conjugate of w dot v, the complex conjugates of each other. And so this is what we want to say here as well. That these almost commute, but if you're working over C, one is the complex conjugate of the other. And then this will all work out. Oh, but wait a second. If this doesn't truly commute, then maybe we can't recover that it's bilinear. Because in order to get those bilinear, we're using the fact that if it's linear over the second term, you can just commute it and it becomes linear over the first term. But now you have this weird conjugate that comes in. So like, let's think about how these two properties combine. Like maybe it won't give us bilinear anymore. Let's think about how these work together. Let's say I want to have some cx plus y in a product with w. What will that equal? Well, first, I can commute, picking up, turn it into its complex conjugate. So it becomes w cx plus y, but it's the complex conjugate of it. And then I can use linearity on the second to say that's just c inner product of wx plus inner product of wy, but it's still the complex conjugate of that whole thing. And then I'm going to commute this again. And so let's think about what happens. This is now going to change to xw. It's going to become the complex conjugate again. So you're going to have the complex conjugate of the complex conjugate. So he returns to his original form. The second guy, when you switch them around, will turn into its complex conjugate of the complex conjugate. So it's back to its original form. But this c still is the complex conjugate. Because c here could be some scalar in c. This is for some c in c. This is when we're working over c. So it's almost bilinear, except when you're working in the first argument, instead of just pulling the c out, in the first argument you pull out the complex conjugate of c. So like it's really close to being bilinear. It's linear in the second argument, but in the first argument, c turns into the complex conjugate of c. So what should we call something? Like it's more than just linear in the second term. It's like linear in the second term and almost linear in the first term. It's like 1.5 linear. So does anyone know the Latin prefix meaning 1.5? Is Devin here? He knows Latin, I think. He was some pretentious high school. Do you guys know Latin? So the university is about to celebrate our sesquicentennial. We were founded in 1874, which means that in 2024, we're a century and a half old. What's the word for century and a half? Sesquicentennial. Sesqui is Latin meaning 1.5. So instead of calling this bilinear, we're going to call it sesquilinear. Let me just emphasize. Only have to worry about this if working over the complex numbers. If your ground field is R, then the conjugate, there's nothing to worry about. It's the same thing. The C complex conjugate is still just C. Over R, it's bilinear. But when working over the complex numbers, it's sesquilinear. Okay, so that's the definition of an inner product. We took a long time building up to this definition, but I wanted to see lots of examples to try and motivate it and try to make it very clear like what this kind of thing is. It's like the dot product, but we can work with lots of other kinds of vector spaces too. If these are matrices, it could take the trace of the transpose of one matrix times the other. If these are functions, continuous functions, you can take the definite integral from some a to b of the functions times together. We'll look at some more examples next time, but let's stop there for now.